the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. This video is the second in a series on vector spaces, or an introduction to vector spaces for linear algebra students. In this video, we're going to focus on subspaces. Now, subspaces, in my opinion, are much easier to deal with than vector spaces. Not that vector spaces are difficult, it's just that when you're introduced to vector spaces, well, you have this veritable long list of axioms that you feel as though you need to have satisfied every step of the way. That you have to prove every single one of these axioms holds for a vector space. And it is actually true. You do need to prove that each one of these axioms holds when you're given a set that is claimed to be a vector space. However, subspaces, not so difficult. But before diving into a subspace, let's just step back a little bit and say that we can collect all sorts of subsets of a given vector space. So somebody hands us a vector space V, and we can just collect a bunch of little elements, and each little small collection is what we'd call a subset, right? Not that big of a deal. And as I state here, this should be obvious as we can assemble all polynomials from P sub n, which is the set of polynomials of degree n or less. We could collect all of those polynomials, let's say, that have degree 2. That is a subset of that set of polynomials of degree n or less. However, it takes an exceptional collection from our vector space to gain the name subspace. And that's what we're focusing on here. So let's start by taking a look at a visualization of a vector space, specifically the vector space F, which is a space of all functions. And then we'll collect some subsets of this vector space. Now the visual I'm going to give here is just a big old box, honestly. So we have this big box that we're going to call F. And F is the vector space, which is the collection of all possible functions over the real number system. So like the cosine of x and maybe like pi times the natural log of x and stuff like that. Now, there are a lot of subsets within this vector space. And by the way, in the previous video, which was on vector spaces, an introduction to them at least, we had proved, sort of, that F was a vector space. So it satisfies all the axioms I had just shown. Well, one subset of this vector space is the set of all polynomials of degree n or less. Some vectors that might be included in that set would be the vector 3x or the vector negative 2x to the third minus x plus 1. There are constants within this subset of F as well. A very specific and special constant that's in this is the 0. And in fact, I actually want to write that elsewhere, so I'll write it right here for a very special reason. Yet another subset of all of our sets of functions is a set of all trig functions. Now I'm not going to put a double bar on that because then it'll just look like, well, like that, and it just looks weird to me. But let's let T be the set of all trig functions, which is a subset of all functions. Now, one such element within that set would be, for example, the sine of x. Another element would be root 3 cotangent of x. And by the way, sums of these vectors would also be within T. For example, cosine of x minus 3 tangent of x would also be a vector within T. So its size is not necessarily less than the size of the set of polynomials of degree n or less. It's just that I didn't want to have to draw in a large space for that. So these are considered subsets of our vector space F. But what makes a subset of a vector space gain the name subspace? Well, we first need to define what a subspace is, and actually in that definition, we'll gain the ability to understand what it takes for a subset to be a subspace. A subspace of a vector space V is a subset, which we're going to call that subset H for right now, of V that has the following three properties. Now I'm just going to read these out and then I'm going to go back through and talk about each one of them in turn and some of the language used here as well. So it's called a subspace, H is, if the zero vector is in H, and if H is closed under addition, and if H is closed under scalar multiplication. Now, if you watched my previous video on vector spaces, then you know I made a big stink about having closure under addition and scalar multiplication. And that is because those two properties are incredibly important. Now let me go ahead and dive into this language a little deeper so you really can gain an understanding of what's happening here. So we have some set H. In fact, let me go to the last picture. We have some set H. For the moment, let's just replace this P sub n with H for the time being. And that's a subset of our vector space F. Right now, I'm only saying it's a subset. So H is just a collection of objects from within our vector space F here. To be called a subspace, H has to have the zero vector, and you could see the H here, which is actually our set of polynomials of degree n or less, but I just changed it to H just to match the definition. But it does have the zero vector. H also has to be closed under vector addition, which is just the same thing as saying is closed under addition, and it has to be closed under scalar multiplication. Now, because H in our example back here is actually the set of polynomials of degree n or less, we know, because we proved it last video, that it's closed under addition and scalar multiplication. So it already has those two extra properties. So it has 0 and it's closed under scalar multiplication and vector addition. That means by definition, H, which again is technically in this case P sub n, is actually considered not just a subset of our vector space F, it's actually a subspace of our vector space F. And that's by definition. Now let's talk about why I have these three conditions. Really, in most textbooks, they'll only have these two conditions right here. They won't have that very first one. And the reason why they don't have the first one is because if H is closed under scalar multiplication, if that's the case, then 0 times any vector in H is actually an element in H. That is, 0 vector has to be in H. So 3 actually already gives us that 1 is true. If 3 is true, 1 is immediately true. So there's really no reason to include 1. However, in the textbook that I use, the author really wants to include that language, that 0 has to be in your subspace, because he wants you to be able to check for that first when somebody says, hey, guess what I have? I have a subspace. And if you don't think it's a subspace, the very first thing you should look for is there a 0 vector in there? If the 0 vector is not in their claimed subspace, then you know immediately it's not a subspace. The 0 vector has to be in there. So that's why the author of the text that I use includes that first condition. But to be honest with you, when you're proving that a collection of objects which exist within some vector space F is actually a subspace of that vector space F, you really only have to prove parts 2 and 3. You don't have to prove part 1 here. And if you notice, I do have a footnote right here, and that footnote at the very bottom of this page just repeats what I just said. Technically, the third statement, which is closure under scalar multiplication, can be used to remove the first statement because it says that 0 times the vector u is 0, or the 0 vector, which is in H, and that immediately is the very first condition. One other thing I want to mention here before we walk away from this definition is that whenever somebody hands you a subspace, it has to be sub to some other vector space. So nobody's going to say, hey, I have this subspace K, without following up by saying, oh, by the way, that's a subspace of this vector space L or something like that. So whenever somebody mentions the word subspace, it's in reference to a larger vector space it's contained within. That's just a requirement. So subspaces do not exist in a void. They have to be in reference to a greater vector space that contains them. So let's take a very basic example. Prove that P sub n, which is the set of polynomials of degree at most n, is a subspace of the vector space F, which is the set of all functions. We already know that P sub n, by the way, is a vector space. We've actually proven that, but that's not part of this question. Let's pretend as though we just walked in the room, we've never seen P sub n before, but somebody says, hey, I've got this vector space. It's the space that contains all functions. And by the way, I'm telling you right now, it's a vector space. And you say, great, thanks. And then they say, by the way, I need you to prove that the set of all polynomials of degree at most n is a subspace of that vector space. Well, the first thing you need to note here is that P sub n is definitely a subset of the vector space F. So I'm going to note that this way. And I don't know if you've ever had a course that contains set notation like this, but this just means P sub n is a subset. It's kind of less than or equal to is what it looks like, right? It's a subset of the vector space F. Now all we need to do to prove that P sub n is a subspace of F is to show that P is closed under addition and closed under scalar multiplication. But luckily, we've already done this in a previous video. In a previous video, we had written that the sum of, ignore the red ink, so we have the sum of polynomials having at most degree n is a polynomial of at most degree n. So therefore we have closure under vector addition for the set of polynomials of degree at most n. So you grab any two vectors from that set, add them up, there's still a vector which is a polynomial of degree at most n, therefore that vector is still in P sub n. So we have closure under addition. And again, from that very same video, I'm just going to erase this red ink here and take a look at closure under scalar multiplication. The constant multiple of a polynomial having degree at most n is still a polynomial of degree at most n. So if you multiply a polynomial by any constant, it's still a polynomial and it doesn't gain degree. It might lose degree, but it doesn't gain any degree. So it's still in P sub n. So we have closure under scalar multiplication. So I'm just going to write here that by example 4.1.1, which is what we were just looking at, P sub n is closed under addition and scalar multiplication. Because of that, P sub n must be a subspace of F. Notice that I did not worry about proving that the zero vector was in P sub n, because there's no need for that. If you've already proven closure under scalar multiplication, it implies the zero vector is within P sub n. That's it. That was a really quick proof, right? Now we get to a theorem that is kind of important. Every subspace is a vector space, and every vector space is a subspace of itself and possibly larger vector spaces. Now, before I read off the proof I just wrote down a few moments ago, let me try to convince you a little bit. Every subspace is a vector space. Well, I happen to know that a subspace of a vector space is closed under addition and multiplication. So it also has the zero vector. So 3 of the axioms in our list of 10 axioms for a vector space are already satisfied. Moreover, because that subspace is actually a subset of your vector space, it adopts a lot of the qualities of the vector space itself. Specifically, the associative, commutative, and distribution properties, which is pretty much every single property. And that's what the proof basically says. Let H be a subspace of the vector space V. That implies H satisfies the closure axioms and zeros in H. So that's what I said to begin with. 3 of the axioms are satisfied. Due to closure, all the other axiomatic properties are adopted from the parent vector space. So all of those axioms are adopted into this subspace because it's closed. It contains all of its additions and stuff like that. And because it exists within that vector space, it adopts all the arithmetic properties and the axiomatic properties, which implies all axioms apply to the subspace, which implies the subspace is a vector space. That's the first part. The second part is every vector space is a subspace. Well, that's actually pretty quick and easy to prove because, and I'll just use language here, a vector space is contained within itself. That is, if I said, what's a subset of this set of numbers right here? Well, a subset of that would be 0 and 1. It doesn't have to be what we would call a proper subset. It could be the same exact set. So in a bigger format, if I gave you a vector space F, let's just pretend, well, that's contained within the vector space F. So that vector space is a subspace of itself because it contains 0 and is closed under addition and scalar multiplication. Now I did that with language, so it's a little bit hand wavy, but there you have it. I find that to be a good kind of language way to do this. And the image that I have down here, that I just drew out here, is that you have some vector space. Let's just call this vector space V sub 1. It's contained with, that's a vector, sorry. That's a vector space V sub 1. And that would be considered a subspace of the vector space V sub 2, which would be considered a subspace of the vector space V sub 3. These are like those Russian nesting dolls, right? Where you keep opening them up and there's something inside of it, right? So these are all subspaces of their parent vector spaces. And they keep shrinking. They don't have to shrink technically because V sub 1 is a subspace of itself. But this gets all the way down to the 0. Let's just pretend this just contains 0 vector, the 0 subspace. And that is actually a vector space as well. The set containing only the 0 vector in a vector space is a subspace called the 0 subspace. So again, looking back at that picture, remember that every subspace has to contain the 0 vector, and every vector space has to contain the 0 vector. So if I had a bunch of containing or nested vector spaces, they would overlap all containing the 0 vector. So I'd kind of zoom in and zoom in and zoom in and zoom in until the smallest such contained space is the 0 subspace. But that's a little more esoteric than we need. What's important here is that you know, if you're handed a subspace, it's a vector space. And if you're handed a vector space, it's a subspace of at least itself, possibly larger vector spaces. So let's take a look at an example here. Is the set of all polynomials of degree 3 or less with integer coefficients, let me highlight that because it's important, is that a subspace of P sub n, which is a set of polynomials of degree n or less? Well, we could probably all definitely agree that it is a subset of P sub n, because P sub n is a very large set containing all polynomials of degree n or less. And we're going to take a slice of that, specifically the set of all polynomials of degree 3 or less. However, a very special condition on this is that we want all of our polynomials that we grab to have integer coefficients. That's a very specific requirement. So I'm going to note that this way, that they're polynomials of degree 3 or less, and they have integer coefficients. That's how I'm going to note that. So for example, elements within this would be stuff like 0, actually. 0 is a polynomial of degree 3 or less, and it has an integer coefficient of 0. Another element within that subset would be something like negative 3x cubed minus 1, and so on and so forth. You get the point. The question is that a subspace? Not just a subset, but a subspace of P sub n. Well, let's consider actually a vector u within this subset. If it's going to be a subspace, then any scalar multiple of that vector u should land directly back into this subset. So for example, 3 times the vector u. Well, since you're multiplying the vector u, which is a polynomial of 3rd degree or less with integer coefficients, by an integer, 3, well then the result is definitely another polynomial of degree 3 or less with integer coefficients. So far so good. However, what if I were to take that polynomial and instead multiply it by root 2. Doing so means I've taken a polynomial, degree 3 or less, with integer coefficients, multiplied each of its coefficients by the square root of 2. The coefficients of the resulting polynomial will no longer have integer values. They will still be in P sub n, which is a set of all polynomials of degree n or less, but they will not be in P sub 3, z, because again, they do not have, or that polynomial specifically that we just created does not have integer coefficients. So therefore, P sub 3z is not closed under scalar multiplication. When you write this down, let's say during a homework or an exam or something like that, make sure you justify your statement. You can't just say, it's not closed under scalar multiplication without providing a counterexample. You have to provide a good counterexample. So I provided one up above. Root 2 times u is definitely not within P sub 3, z. So therefore, P sub 3z is not closed under scalar multiplication. Hence, P sub 3z is not a subspace of P sub n. That's kind of the final statement. You definitely want to state that for your reader. If H is a set of all points in R cubed that satisfy x squared plus y squared minus z squared is equal to 0, can we show that that's a subspace of R cubed? Again, H is a set of all solutions, basically, to this equation right here. Well, I'm going to go with a big fat no, that set of points of all solutions to this is not a subspace of R cubed. The very first thing I'm going to try is to see if 0, 0, 0 is a solution, because if it's not, then H would not be a subspace of R cubed because the 0 vector would not be in H. Unfortunately, 0, 0, 0 satisfies the equation, so again, the 0 vector is in H. All right, well then maybe what I want to do is see if I can get a couple solutions to this and see if their sum is a solution to this. That actually is probably the kicker here. So let's create a couple solutions just very quickly. For example, 1, 1, let's see, that'd be 1 plus 1, which is 2. So I need z to be root 2. So we definitely know 1, 1, root 2 is a solution, and that means that 1, 1, root 2 is in H, which is our set of solutions. Now let's create a completely different solution. And the completely different solution I'm going to create here is, let's say 2, 3, and something else. Actually, something that one of my students had noticed with this, which I thought was pretty awesome, is that it's sort of like the Pythagorean theorem if you added z to both sides. And so they came up with 3, 4, 5. So I think I'm going to steal that. So let's suppose we have the possible solution of 3, 4, 5. And I say possible solution, in reality, it is a solution. There's no possible about it. It is definitely a solution. So since we have these two different vectors in H, let's see if their sum is also in H. If their sum is not in H, then we know this is not closed. H is not closed under vector addition. Add those two vectors up and you get 4, 5, 5 plus root 2. Let's see if that satisfies the equation. I can tell you right now, because we have a radical and there's nothing to offset that radical, that will not be 0. And therefore, the sum does not satisfy the equation. That implies immediately that H is not closed under addition. And that implies H is not a subspace of R cubed. So that's a pretty good counterexample problem as well. You always want to look for the easy counterexamples, especially if you have powers greater than 1, then using or providing a counterexample to the closure under addition property should be viable. The following theorem is provided without proof for a couple of reasons. 1, this video is already very long, and 2, you usually see this proof in your textbook. So suppose we have some vectors, v1 through vn, and they're vectors in a vector space V. Then the span of those vectors is a subspace of V. Verbally, the proof goes like this. S is the span of all of these vectors. That is, S is the set of all linear combinations of those vectors. So if you took any of those two vectors and added them up, that sum has to be in the span. That is, it's closed under vector addition. Also, if you take any vector, v sub 1 for example, and multiply it by 10 or any number you want, because S is any linear combination of those vectors, one such linear combination is that constant that you just multiplied v1 by plus 0 of everything else. So this is closed under vector addition and scalar multiplication. Therefore, the span of a set of vectors is a subspace of the vector space V if those vectors are from a vector space V. So again, you have some vectors from a vector space V, the span of those vectors is going to be a subspace. And this is where I'm going to stop the video because there's really not much else I can do. I could, but all I would do is exhaust every single problem you could see. And I just don't want to do that. I want to leave some problems up to you. So I hope this introduction to subspaces seems okay for you. Remember, it all comes down to just proving that your supposed subspace is closed under addition and scalar multiplication. Or if somebody gives you a claimed subspace and you don't think it is a subspace, show that either 0 is not in it, so therefore it's not a subspace, or that it's not closed under addition or under scalar multiplication with a counterexample. Once you have that counterexample, you have then proved it's not a subspace of the vector space you were given. Anyhow, I hope you have a wonderful day. Be a great human.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way. Cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Says, listen close, don't talk too much that isn't cold. Sure, you may really hurt inside. It doesn't justify you to speak too loud and cry.